So as we said last time about the running time of the brute force algorithm for computing distances, is that we got a very complicated formula, but at the end, what we could say also, one of the things that we could say without going through all these complications and details, is that the running time of that algorithm is at least 2 to the n minus 1, if you remember. We said because the algorithm was going to try every possible subset of size n, every possible subset of a set of size n minus 1. And it was going to inspect each one of them and do a lot of work. So even it's going to do definitely more than 2 to the n minus 1. But we could say that we can put a lower bound on the running time that is 2 to the n minus 1. Now, why does that matter? Because we have shown already that when we talked about growth of functions, that 2 to the n is growing actually very, very fast, that even when n was 256, it would take 10 to the 59 years for a computer that can handle 10 billion operations a second. Okay? And 2 to the n, 2 to the n minus 1 are basically the same. It's just that one is divided by 2. Okay? So using this kind of technique by putting lower bounds and upper bounds on an algorithm is very helpful because, as I said from the beginning, that we are not trying to get at the exact running time of the algorithm. We are trying to get an approximation that gives us a good idea about how long that algorithm would take once we implement it. So in the case of brute force algorithm, using that kind of technique by bounding the running time from below, it told me that this algorithm is going to take at least exponential amount of time, 2 to the n, on the order of 2 to the n. And that's enough for me to know that this algorithm is not practical, is not worth implementing and giving to the user. In the same sense, also, we can usually put an upper bound on the running time so that we get an idea of how much time is this algorithm going to take in the worst case. Okay? So how fast is this function going to grow? When we have a function like 5n plus 3n squared minus 17n cubed minus 19 to the 17, that's a function that we have to start plugging in values of n to evaluate it. But if we use this kind of lower bound and upper bound technique, we can get an easier function that we can understand better. It's much easier to say 2 to the n grows fast and look at a function like 2 to the n and decide that it grows very fast than a very complicated function that has summation and combinations, n choose k and n factorial and so on. Okay? So for that, there is a set of mathematical tools that we use, which we refer to collectively as asymptotic notations. Asymptotic notations allow us to put upper and lower bounds on functions, as well as the two bounds at the same time. That will bound these functions and will give us an idea of how fast the function grows, how bad can it be, or how good it can be as well. Okay? So I will start with the first one of there are three main asymptotic notations that we will use. The first one corresponds to putting an upper bound on the running time of an algorithm. So if I have an algorithm, I have analyzed the running time of an algorithm, and I get a function of the input size. So we'll assume that the input size, the parameter that corresponds to input size is n, and I will assume that I have done all my work, and I got that the running time is f of n. Okay, some function of n. Okay, now I can plot this function as a function of n, and this is f of n here, and it grows like this. Okay, so this is f of n here. Okay, this is actually, let's call this y here, because we can plot different functions. So this is a function f of n, but again, f of n might be, let's say, for example, f of n might be like, million plus 1,000 n plus 3n squared. Okay? Now I want to put an upper bound on this function. Okay? I want to put an upper bound on this function. I want to basically to get another function that once I plot it here, or I compare it to f of n, it will grow faster than f of n after some point. Okay? So in the asymptotic notations, when I have a function f of n, I am interested in getting a function g of n. getting a function g of n, that except for a few values of n in the beginning, after a certain point, the function f of n is going to grow at most as fast as some constant times that function g of n. Okay? So remember, again, in asymptotic notations, I have f of n. It's a function that someone analyzed the running time of an algorithm and obtained. Okay? Someone analyzed the running time of certain algorithm, got the function of f of n. I am interested in quickly getting some sort of upper bound on that function so that I can understand how bad can it be. Okay? Now, in asymptotic notations, we are interested in getting another function g of n that will bound f of n from above. That when I draw them, g of n is going to be on top of f of n. But again, with the caveat that if multiplied by a constant c. Okay? So there is a constant c here that if I multiply it by g of n, it's going to be higher than f of n. The other issue, as I mentioned, is that in the beginning, I can tolerate a few values of n, because remember that we focus on the growth of function as n goes to infinity. I am not much concerned with what happens when n is very small. Okay? So when we talk about putting an upper bound, we are interested basically in this function g of n, and we have to think about two constants at the same time. One constant that we are going to call n0, and the other constant that we are going to call c. And we want that function g of n such that, except for these values here smaller than n0, or for every value of n greater than or equal to n0, for every value here, I want f of n to be at most c times g of n. Okay? Or in other words, we want a function g of n such that there exist two constants c and n0 where f of n is at most c times g of n for every n greater than n0. Okay? Again, if we look at this picture here, it shows clearly that if you ignore all the values of n that are smaller than n0, if you ignore them and just focus on values of n greater than or equal to n0, you will notice that f of n is always smaller than c times g of n. And this is what this definition is saying, that we have a function g of n, two constants c and n0. C has to be strictly greater than 0. n0 is greater than or equal to 0, such that f of n is smaller than or equal to c times g of n for every n greater than or equal to n0. This upside down a, basically in English we say for all, or for every value of n that is greater than or equal to n0. If we have this scenario, we have a term for it. We say that in this case, f of n is big O of g of n. And this is the first asymptotic notation I'm introducing, the big O notation. F of n is O of g of n if we have this scenario. Or if I can find two constants c and n0 such that for every n greater than or equal to n0, f of n is going to be at most c times g of n. Okay? So this is the first notation that we can use, and it allows us to put an upper bound on the running time of an algorithm. Again, in this notation, we will ignore a finite set of values in the beginning and focus on the running time as the input size grows. Okay? So this is the first asymptotic notation we learn, and again, it's about putting an upper bound. This is the definition. If you want to put an upper bound on a function f of n, you find a g of n and a c and an n0 that will satisfy this definition. Okay? In the case of the brute force algorithm that we devised for the distance problem, we actually looked at the lower bound. We said that that algorithm will take at least 2 to the n amount of time. So what does it mean to put a lower bound? We can look at the same thing, but we can think about g now, c times g of n being a lower bound on this. And in this case, we can think about it as I can think about it as the following. If I have f of n like this here, and I can find a g of n, for example, c times g of n, and I can focus on the n0. So now I found a function g of n such that f of n is going to be greater than or equal to c times g of n once n is greater than n0. In this case here, again, it's similar definition. We need to find a g of n and two constants such that f of n is greater than or equal to c times g of n for every n greater than or equal to n0. In this case, we say that f of n equals omega of g of n. Okay? So omega is for lower bound. Okay? The third asymptotic notation is that I can take this function, f of n, and now I can bound it from below and from above by two different constants multiplied by the same function g of n. Okay? So we have now c1 times g of n, and we have c2 times g of n. And I say f of n is bounded from above and below by g of n times two different constants. In this case, what we have is that f of n is, we say it is theta of g of n. It is sandwiched between c1 times g of n and c2 times g of n. So we have these three asymptotic notations. F of n equals theta of g of n, f of n equals big O of g of n, and f of n equal omega of g of n. This puts a lower bound, omega puts a lower bound, big O puts an upper bound, theta sandwiches the function between a lower bound and an upper bound. And these are the asymptotic notations that we will be using in the course, and mainly we will be focusing on an upper bound.